here? Okay, so the vector part is carried by these two univectors, right? So what's the dot product between x hat and minus x hat? Okay, so one of them's pointing that way and has length 1. The other one's pointing that way and has length 1. Or, if you prefer, pull this minus sign out like that. And this is the dot product of a unit vector with itself. So, has length 1. Good question. Other questions? Huge. Why the work done by gravity on the particle is not negative. Somebody? Sure.
Well, gravity's pulling down, it's moving down, so they're in the same direction.
Gravity is pulling down, it's moving down, they're in the same direction, the dot product is positive. So if we're asking what is the work done on the particle by the external force of gravity, since they align, it's positive. But I hope that makes sense, because what's happening as it falls? It's converting gravitational potential energy into kinetic energy. So it's losing gravitational potential energy. But in terms of just thinking about work, gravity aligns, and so it does positive work, which boosts the kinetic energy of the particle. Then the spring does the opposite. The spring pushes against the motion, and so now the kinetic energy that got stored in the motion of the mass is converted into the compression of the spring and stored as potential energy, sometimes called elastic energy in the spring. Yes?
Why did you look at this in terms of work instead of in terms of energy?
Just because I wanted to start from where we left off, which was work energy, and remind people, where does that come from? That came from considering what changes kinetic energy. And I was fielding a question from one of the AE tutors, Jaron, about, okay, what is the right way to think about, I forget which homework problem, but I want you to recognize, and it's on the previous slide, I think, that all we did to get the work energy theorem was ask, nicely, what is the time rate of change of kinetic energy, and use calculus. This time I did it a little bit faster. I didn't write out the components, but we saw that it's the same. And so that's really going back to the fundamentals. If we define kinetic energy as 1/2 mv squared, then it must follow, just by using F equals ma, this definition of work, and that the change in the kinetic energy of the mass is equal to the work done on it. Okay, and this is another example. We talked about this once before. How do I read a d something? Sometimes we say the little change in, and sometimes we say, what? A little amount of. So I would argue in this one, the change in the kinetic energy is equal to a little amount of work, because the work is characterizing the path, and the change in kinetic energy is characterizing the endpoints.